We've been talking about slope as the vertical distance divided by the horizontal distance. And the examples that we started with are the idea of a flat road, which has zero slope, a hillside, which has a moderate slope, and then a very steep hill, which has a very steep slope. However, obviously, when we're dealing with real hills, the slope of the hill changes. If you look at this hill, we're in the valley between the two hills. It's flat. There is no change. So the slope is zero here. Then as you go up the hill, the slope increases for a while till you get it to a maximum slope here because it's going up more steeply here. And then as you get up near the top, you go back to a zero slope because the top is pretty flat. This is typical of the problem that we have with a lot of data curves. In this case, what I'm going to talk about is a car accelerating. What happens when a car accelerates, because of the definition of the word accelerate, is that it keeps going faster and faster. Now I'm going to expand this so that we can see what's going on a little bit better. And as you can see here, the car is accelerating at a constant rate, 8.82 meters per second. Now what that means is that for every second, the car is going faster by 8.2 meters per second. Meters per second is a velocity. Meters per second is an acceleration. And if we look at the velocity at the end of each time interval, you can see what happens. It starts out 0, and then over 3 seconds, it increases to 26.5 roughly meters per second. Now, if you look at the total distance, which is what's plotted here in blue, what's happening is that it's going up, but it's not going up at a constant rate. In the first second, the velocity, the total distance goes up by 4.41 meters. In the second second, it goes up almost 3 times as fast, 13.23 seconds. So what's going on here is that's what's causing this rising curve of the total distance versus time. And it's simply because in each second, the car goes a longer distance than it did in the previous second. So that means that our slope is constantly changing. And this is typical for a lot of curves that you'll run into in mathematics. We still can get the velocity, but we can only get it at each point because each point is different. So let's put some lines in here so that we can figure out what the slope of the curve is at any point, and that will give us the velocity. So let me get some lines here. I'm going to have one line here. And you see what I'm doing is I'm making this line, which is the slope, just at and tangent to the curve at the point that we want to measure the velocity. Tangent to means that the line just touches the curve at that one single point. And if you think about it, that is the slope of the line at that point. So we have this now. Now, let's figure out what this slope is. All right, we're starting here just after 1/2 second. See, these minor divisions are at quarter-second intervals. So we're starting out just after 1/2 second. Now, in order to measure the slope, what I've got to do from the definition down here is I have to figure out the vertical distance and then divide it by the horizontal distance. Now, to make it easy, what I'm going to do is I'm going to have the horizontal distance just be 1 second. So I'm starting out a little after 1/2 second here. I'm going to go out to a little over 1.5 seconds here and measure what the vertical distance is at that point. So let me get another line here so that we can see what we're doing. So I want it about there. And I'm going to bring it up so that it's vertical so that we can measure it. All right, so that is my estimate of where it is. Now, obviously, these are just guesses because whether this line is exactly tangent to it or it's sloping a little bit different, yeah, I can't tell that. But it's pretty close. So now now what we're going to do is we're going to calculate the slope. The vertical distance is this distance here. Okay, so that puts us, I don't know, someplace around like 9 or so meters. Okay. The horizontal distance is in second, and we adjusted it so that it was exactly 1 second. So that gives us our velocity, as good as our estimate is, here at 9 meters, the vertical distance, per 1 second, the horizontal distance, or 9 meters per second. Now we can check ourselves because we happen to have the data right here. So this is exactly at the 1 second mark. If we go up to the 1 second mark and we look at the velocity, the actual velocity is 8.82 meters per second. We guessed at 9 meters per second. That's pretty good. If I was going to look at the slope at this next point, it's going to be much steeper. Okay, so what I've got to do is I have to adjust my tangent line here. Okay, and this, a little fiddling around to make this work, of course. Now, you can see that this slope is considerably steeper than the previous one. Okay, and if this one, luckily, it turned out to hit at about the 1 second mark. At the 2 second mark, which is 1 second later, I'll just move this over here to line up with that. So this is 1 second horizontally, so that's our horizontal distance. Remember, we're using 1 second because it's easy to calculate with. So the horizontal distance, that is the numerator of this, is 1. The vertical distance is just the vertical distance here, and that's, I don't know, someplace around, this is about 17.5, so we're probably right about there, someplace around 17.5, 18. And if we actually look at the data up here for the 2 second mark, because remembering we're calculating the slope at this point. This thing is tangent to the slope right at the 2 second mark. So we come up to the 2 second mark and actually look at the data, and it's 17.64 seconds. We estimated about 17.75 seconds. Again, for doing an estimate, that's pretty good. So anyway, this is the answer to how you calculate slope for a curve. It's not a single slope. You have to look at the slope at each point of the curve, and it's constantly changing.